Okay, problem number 2, a qualitative quantitative translation problem, says that a soccer ball is kicked at an angle of 38 degrees above the horizontal with an initial speed of 14.3 meters per second. So there's the ground, and here is the soccer ball, and its trajectory, something like that. So we know that the initial speed is 14.3 meters per second. That is the speed at which the soccer ball is initially leaving the ground at some kind of an angle, and this angle is 38 degrees. 100% of the time, when you draw a vector at an angle, you want to figure out the two components of that vector. There is a horizontal and a vertical component to that initial speed. This vertical component is equal to 14.3 meters per second times the sine of 38 degrees, and that comes out to be 8.8 meters per second. The horizontal component is 14.3 meters per second times the cosine of 38 degrees, and that comes out to be, let's see, 14.3 cos 38. That is 11.3 meters per second. So the initial speed at which the projectile is launched is 14.3 meters per second. There's a horizontal component that's larger than the vertical component. Those are some things you can do immediately before you even tackle what the problem says. Another thing that you can always conceptualize is that this problem has two halves. There's the time it takes to get to the top and the time it takes to get back down to the bottom. And those two things are symmetric. Also, the distances from the launch point to the midpoint and from the midpoint to the end, those happen to be the same. We want to determine first what the maximum height of the ball is. Now, nowhere are you prompted to calculate the time, but it turns out the time of flight is very, very important. And for this projectile, because it's launched initially vertically upward, you have some initial vertical velocity, call that v naught y, is 8.8 meters per second. It gets to the top where its velocity is 0. The acceleration rate on the way up is negative 9.8 meters per second squared. With that information, you can calculate the time that it takes to get to the top. So the time is equal to the delta v over a. The change in velocity is 8.8 meters per second, negative 8.8 meter per second, over the acceleration, negative 9.8 meters per second squared. That'll get you a time, 8.8 divided by 9.8, 0.898 seconds. Another way to express that is with that equation that I derived for you like a week ago. T up is equal to the vertical velocity divided by the acceleration, and the vertical velocity is equal to the initial velocity at the angle times the sine of the angle divided by g. That'll also come out to be 0.898 seconds. So although the problem doesn't prompt you to calculate the time it takes to get to the top, that time is very useful. The ball's maximum height can be found using that time it takes to get to the top in one of two ways. One way is that the vertical distance is equal to v naught t plus 1/2 at squared. You could use that equation, but you could also, without the time, calculate the maximum height with the equation v squared is equal to v naught squared plus 2a delta y, where delta y is the change in height, a is 9.8 meter per second squared, the velocity at the top is 0, and the initial velocity is the vertical velocity, 8.8 meter per second. There's also the equation that I derived for you, the y max equation, but here delta y, the change in height, would be v squared minus v naught squared divided by 2a. The final velocity is 0 at the top. The initial vertical velocity is 8.8 meters per second. That quantity is squared, divided by 2, and negative 9.8 meters per second squared, because we expect delta y to be some positive value. So let's see, 8.8 squared divided by 2 and 9.8 is 3.95 meters. There are only two significant figures because the 38 degrees only has two significant figures. So 4.0 meters would be good for the maximum height. B, the ball's final velocity. Now it's important that you're prompted for the velocity. The velocity at which it lands has the same speed at which the object takes off, 14.3 meters per second. But that's only a speed, because speed just tells you how fast. A velocity has to include a direction. So you could say 14.3 meters per second, 38 degrees below the horizontal. It's not appropriate to say southeast because that's not necessarily the direction, but it's some angle below the horizontal. What's the velocity of the ball at the apex of the flight? So when the ball is up here, that's the apex. The velocity is only horizontal, and that velocity at the top is a horizontal velocity, and it's the same as what it was the whole time. Turns out that it's 11 meters per second. It's the horizontal component of the initial velocity. The ball's range, because the horizontal velocity is constant, the horizontal velocity is equal to the distance divided by the time. The horizontal distance is then equal to the horizontal velocity times the time. The horizontal velocity is 11.3 meters per second, and the time of flight is twice the time it takes to get to the top. So if it's 0.898 seconds to the top, the total time is 2 times 0.898 seconds. And so that comes out to be, with two significant figures, 20 meters. The range is a horizontal distance of 20 meters. So there are alternate ways to get the same answers, but those are all correct answers. The velocity at the apex is 11 meters per second, and that's only a horizontal velocity. The range is 20 meters. The velocity at which it hits is the same speed at which it takes off, 14.3 meters per second, 38 degrees below the horizontal, and the maximum height that it reaches is 4 meters. Now, the graphs that are associated with that motion can be displacement, velocity, and acceleration time graphs in both the horizontal and the vertical dimensions. So in the horizontal dimension, we know we travel a distance of 20 meters. So here at the bottom, this is always 0. We'll make this 20 meters at the top. And this time, 1, 2, 3, 4. We'll make this 1 second. Make this 2 seconds. So the total time of flight is about 1.8 seconds. And we end up with a speed of 20, or a horizontal distance of 20 meters. So the horizontal displacement has a constant slope because the horizontal velocity is constant. The horizontal velocity has a constant value. Let's see, that's 0. We'll make this 1, and then 2 here. The horizontal velocity is constant at 11.3 meters per second, or about 11 meters per second. And the horizontal velocity is constant for all 1.8 seconds. And the acceleration in the horizontal direction is 0 for all that time. So let's see, that goes to here. This is 0. This was 1 second. Let's see, 1, 2, 3, 4. 1 second is here. And then 2 seconds is right here. The acceleration is 0 in the horizontal dimension. Now in the vertical dimension, things are more complicated. The maximum vertical displacement is 4 meters. I don't want to make that go too high up here. I'll call that 4. And this is 0 down here. 2, 3, 4. This is 1 second. And that's 2 seconds. So you begin at a position with a y position of 0 at the beginning. After 1 second, it's at a position of 4 meters. Oh, that's 0.9 seconds, 0.898 seconds. And then after 1.8 second, it's back down to the ground level. And this motion is going to be like a parabola. Let me try to redo that. Since the slope of the line on the displacement time graph is the same as the velocity, here you have a large slope at the beginning, indicating a high velocity at the beginning. The velocity in the vertical direction is 0 at the top, and the slope increases as the vertical velocity increases in the y dimension. What's important in the y dimension here, this is 1 and this is 2, is this velocity here we'll call 0. So here I'll put a line across for a velocity of 0 the whole way. The initial vertical velocity is positive, and it's positive 8.8 meters per second. Now I'm just going to sketch it here. I'll put this position and call this positive 8.8. and that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Make this negative 8.8. So the velocity begins as positive 8.8 meter per second, and then it ends up as negative 8.8 meter per second at a time of 1.8 seconds. The slope of this line is g, negative 9.8 meter per second squared. The velocity is positive. It decreases to a velocity of 0 at a time of 0.9 seconds. That's when it's at the apex. This is the vertical velocity, and then the velocity becomes negative and ends up at negative 8.8 meter per second at a time of 1.8 seconds. The acceleration rate for the entire bit of motion for the projectile is negative 9.8 meter per second squared. So here I'm going to put a line on the graph indicating a value of 0, and it doesn't really matter where. We'll just call this negative 9.8 meter per second squared, and that happens for, let's see, up to 1.8 or 1.9 seconds. So like, or 1.8 seconds, just like that. So the velocity or the acceleration rate is negative 9.8 meter per second squared in the negative direction, or in the y direction, for all 1.8 seconds. So that's how the graphs go. That's number 2.